Welcome back. In the last class, we discussed about, we started discussing about strong and weak coupling spins. We discussed more about weakly coupled spin system in the homonuclear case and in the heteronuclear case, and also in the labeled system. Even in a molecule, naturally abundant molecule which is 1% abundant carbon or 0.37% abundant nitrogen, you can label them and bring in the heteronuclear coupling or homonuclear coupling in molecule like CC coupling or CN coupling and measure the couplings. Because the heteronuclei, what is going to happen is their chemical shape separation is of the order of megahertz. As a consequence, they are all weakly coupled spin system. So this is few example I gave you, and one of the most important condition I said, the chemical sheet separation should be sufficiently larger than J coupling. I even showed you the delta by J coupling should be greater than 50. If you take the reverse order, J over delta, it must be much smaller, point less than 0.00101 like that. Then these coupled spin systems are called weakly coupled spin systems. Why I am telling all those things? What is so? You may ask me a question. So what if it is strongly or weakly coupled? How does it matter? Please remember, I'll go ahead and show you. Weakly coupled spin system are easily amenable to first order analysis. What I mean is directly you can assign and get the chemical sheets and J coupling. But in strongly coupled spin system, you cannot do that. It is not possible. Okay, so we should know what is weakly coupled and what is strongly coupled for analysis. Now I'll introduce today what is strongly coupled spins. What are strongly coupled spins? The chemical sheet difference, it is exactly opposite of weakly coupled. What you have understood for weakly coupled, make a reverse of it, it is strongly coupled. Their chemical sheet separation was much larger than J coupling. Now in this case we say this is almost comparable to this coupling, or it can be 0, no problem. Then chemical shift separation, then it is an even strongly coupled spin system. I'll show you later when we go ahead. So this is a strongly coupled spin system. One of the important condition is the chemical shift difference between two coupled spins must be much smaller, and it is comparable to that of J coupling. Remember, J by delta in the previous case was less than 1, 0.001, but here it is more, much larger than 1. In the other case, delta J was approximately 50 or even more than 50 I said, but it is less than 1 here. So these are the cases when you come across such a situation, it is called strongly coupled spins. These are all spin systems, so strongly coupled. Okay, give you an example of a strongly coupled spin. Look at this proton. This is a thiophene system substituted by two bromines. JHH between this proton and this proton. Okay, this is of the order of 1.6 hertz. See, this is 1.6 hertz. What is the chemical sheet separation? Is only 4 hertz at 200 megahertz. Doesn't matter, you go to even 500 megahertz, even then it is 10 hertz. At 500 megahertz, if you go to even 1 gigahertz, it can become only 15 or 20 hertz. Now take the ratio between J over delta or delta by J. It doesn't fit into your weakly coupled spin system equation. Now this separation, chemical sheet separation, is almost of the order of J coupling. What does it mean? It means these two spins are strongly coupled. This proton and this proton are strongly coupled. Let us take the example of two protons here and here. They are also very strongly coupled spin system. Okay, these are all simple examples to show the definition of strong coupling and weak coupling. But in NMR jargon, there is a notation to define the strong and weak coupling. Okay, this is called Pople notation. Remember this word, it is called Pople notation. What we do in the Pople notation is a very simple logic. Please understand this very carefully. Each spin of nuclei in a coupled spin system, and you know what is a coupled spin system, I've already discussed long ago. In a coupled spin system, each spin of nuclei is assigned a capital letter of the Roman alphabet. What is the meaning of that? The meaning of that is, I am going to say, we take only A, B, C, D letter alphabets. A, B, C, D up to Z you can go. No problem. Each spin of nuclei is assigned a letter. So what? How do you assign it? Next question. Letters with short distances in the alphabets indicates strongly coupled spin system. Letters which are far away in the alphabets indicates weak coupling. Very good definition, right? Now, let us say I have two protons here, one proton and another proton here. They are coupled. If I call this as A and if I call this as X by nomenclature using Pople, it means this chemical shift separation of this and this are far away separated compared to J coupling between these two, compared to J coupling. So what does it mean? It means these two protons are weakly coupled, very weakly coupled. On the other hand, I have a proton here, I have a proton here. And I'll write it as A and I write it as B. What does it mean? The chemical shift separation here between this and this is almost comparable to coupling between A and B. It is a strongly coupled spin system. Please remember, if the letter, if you are representing the interacting spin, coupled spin system by a Roman alphabet, if the letters are written far away in your alphabet order, in which case they are weakly coupled if you take far away. If you take next to each other, it is strongly coupled. For example, A, M, X spin system. Remember, I analyzed the three spin system spectrum AMX. We showed 4 peaks for A, 4 for M, 4 for X. We also understood, I wrote down energy level diagram and looked at the transitions, everything. I said it is weakly coupled at that time. I remember that. That means the letters A to M is far away compared to other letters. M into X is far away. In between there are many letters. That shows if the three spins are weakly coupled, I can write A, M and X. If only two are coupled, A and X. If four are coupled, I'll say A, K, P, X. That is a four spin weakly coupled. Now on the other hand, if I say I have two spins which are strongly coupled, I'll write AB. I'll write three spins strongly coupled, I'll write ABC. This is the nomenclature. For strongly coupled, you have to write alphabets next to each other. This is a simple thing. Now, of course, we will go more into that. There are a lot more to understand. Now we will see here. Weakly coupled are assigned letters like this: AX, AMX, AMPX, etc. In general, spectrum of weakly coupled spins are amenable to first order analysis. This is my definition I told you. It means if I give you a spectrum, simply looking at the spectrum, you can assign and get chemical shift values and coupling values straightforward without doing much of any mathematical operation, computation, etc. That is first order analysis. Second order analysis is little difficult. So this is first order analysis. AX spin system, if I take homonuclear, I told you this is AX. Already I gave you an example of this. And weakly coupled AMX is like this. I took a hypothetical example. I took chlorine, bromine, iodine in symmetrically substituted benzene. Then there are three protons here. This proton and this proton and this proton have their chemical shifts far away separated. It is a weakly coupled spin system. So what I am going to say, I am going to write it as weakly coupled homonuclear AMX spin. Heteronuclear AMX, look at this molecule. I have proton here, carbon 13 labeled and fluorine. What is fluorine? It is 100% abundant nuclei. This is 100% abundant nuclei. Carbon, I label it, let us say. That's also 100% now. I have made it 100% carbon 13. Some chemistry, I labeled it. Now what happens? Remember I told you, heteronuclear spin systems are all weakly coupled because chemical shift separations are so large because the resonating frequencies are far apart. As a consequence, in this case, these three nuclei are weakly coupled heteronuclear AMX. Strongly coupled now, let us say how we describe. I told you, you represent it by the letters which are crows in the alphabet. And you cannot analyze this by a first order method. Straightforward analysis is difficult in strongly coupled case. Please remember this point. Now I'll give you an example of strongly coupled. Take a molecule like this. A, B and C, D. I'll record a spectrum at 100 megahertz or 200 megahertz. You know what happens? This chemical shift separation is much smaller. This to this is smaller, and this to this is smaller, and this to this is also smaller, and this to this is smaller. So chemical shift separation of the protons among themselves is much smaller or comparable to the coupling constant. For example, coupling constant between this and this is 8 hertz, this and this is 8 hertz, this is 8 hertz. Between this and this is 1.5 hertz. So if the chemical shift separation is comparable to coupling constant, then I represent this as strongly coupled ABCD spin system. Okay. Look at this molecule. This is a classic example. This proton, this proton, this proton, and this proton all have nearly similar chemical shift. Goes by. So chemical shift separation is not much larger compared to their coupling constant. Then this is a very strongly coupled ABCD spin system. Okay. Now I was so far taking spins which are standing alone, like see one proton, one carbon, one nitrogen, like that. But in reality, in your molecule, it so happens there can be chemically equivalent groups present. There can be CH3, there can be CH2. Then how do you represent by alphabets? How do you use Pople notation for that? In which case, remember, for chemically equivalent protons, why did they come to chemically equivalent? Okay, chemically equivalent protons, not this. Okay, chemically equivalent we'll talk. Forget about magnetic equivalence and other later. For chemically equivalent protons, the prime notation is used. First thing. Forget about magnetic equivalence. We'll come to that later. And equivalent groups of spins. Take an example. For weakly coupled case, we use a prime, AA prime, XX prime, AA prime, MXX prime, etc. What is this XX prime, AA prime? Don't get confused. I'll give you an example. Similarly, strongly coupled, you use AA prime, BB prime, like this. What do you mean by AA prime here? It means AA prime means, okay, we will take this one. AA prime means there are two protons or two spins having the same chemical shift. Chemical shift is same because the chemically equivalent. Remember that one. They are chemically equivalent. These two protons, but there is a coupling between them. Coupling is not zero. Only chemically equivalent. In such cases, when the chemically equivalent has same chemical shift, use a prime notation. Similarly, X and X, what does it mean? There are two protons which are far away from this A. Far away from A, there are two protons having the same chemical shift again. That's chemically equivalent. Then you have to use prime notation. You call those two spins as X and X prime. Same way, you can write for strongly coupled A prime, BB prime, ABC, AB prime, AB, all those things you can write. I give you an example. You will get more clarity by taking an example. Consider a molecule like this, 1,2-dichlorobenzene. This is the symmetry axis. What is the meaning of that? This proton and this proton are chemically equivalent. This proton and this proton are chemically equivalent. Now, how many types of protons are there in this molecule? There are only two types, because this and this are same, this and this are same, chemically equivalent, give one peak. This will give one chemical shift, this will give one chemical shift. That's all. But coupling is not zero. There is no coupling between this and this is not absent. Coupling between this and this are not absent. It means they're chemically equivalent, but not magnetically equivalent, of course. We'll now worry about those parameters later. But remember, now this and this are chemically equivalent, this and this are chemically equivalent. Now, how do I represent this using Pople notation? Simple. If I call this as A, I call this as A prime, because there exists a coupling between these two. If this I call B, I call this as B prime. Simple. I use the notation because chemical equivalents are there. I can use notation. And between these two, what do you say? This is A, this is B. Means these two protons are strongly coupled. These two are also strongly coupled, but they're chemically equivalent. These two are also strongly coupled. B and B prime means strongly coupled, but they are chemically equivalent. Remember, these two are strongly coupled, chemically equivalent. These two are strongly coupled, chemically equivalent. So you write notation like this: A prime, here B, B prime. But these two are strongly coupled, but not chemically equivalent. They write a different letter, A and B. Okay. You understand how do you write a Pople notation for strongly coupled, chemically equivalent spins? I suppose you are catching my point. Okay. Consider this example now. Metachloroiodobenzene. I hypothetically have written the molecule. This is the symmetry axis. Now what is going to happen? This proton and this proton are having the same chemical shift, chemically equivalent. This and this are chemically equivalent. So I call this A and A prime, and I call the other one B and B prime, provided the chemical shift separation between these two are comparable to this coupling. If by some reason these two protons, let us say, resonate far away, what do I do then? Then I call it as AA prime and XX prime. Between these two they are strongly coupled. Between these two they are strongly coupled, and between them then it will be weakly coupled. See, in a given system, you can come across one or two protons can be very strongly coupled, and between them, between that coupled proton, strongly coupled, and with the other one there may be weakly coupled. Fantastic. Many things can happen. So in this example, here also you take it, this and this are strongly coupled. This and this are strongly coupled. This and this are also strongly coupled. By some reason, this and this become weakly coupled, this proton and this proton. AA prime becomes weakly coupled to BB prime. Then I call it X prime. Understand? Equivalent system always use notation, but the nomenclature of weak and strong coupling remains same. If it is strongly coupled, use the nearest neighboring atom or neighboring alphabet. If it is weakly coupled, use the alphabet which is far away in the list of alphabets. That is important thing you must understand. Now, let us take this example. What do you call this spin system? It is a very simple molecule. Okay. Now this fluorine and this fluorine are chemically equivalent. There is a symmetry along this axis. And this proton and this proton are chemically equivalent. What is the resonating frequency of fluorine compared to proton? Several megahertz away. I told you heteronuclear spin system are always weakly coupled. It can never be strongly coupled, right? So what do you call this spin system? A prime, X prime. Why I call it A prime? Because there exists a coupling between these two. If there is no coupling, it is a different nomenclature. I'll come to that later. Because there is coupling between these two, but they are chemically equivalent, I use the notation A prime. Similarly, for this I used X. You are all with me how to use the notation. Now when I have a group of chemically equivalent protons like this, earlier there were only individual chemically equivalent protons. Now if I take a group like this, CH2, CH3, etc., then how do you represent using alphabet? Very simple. In which case, for strongly coupled, you write AB2, where the B2 represents the number of protons in that group. If you say AB3, it will tell you number of protons in that group. For example, this is a H3 group, this is something else. Okay, take this as CH3 group or CH2 group here like that. Okay. For the weakly coupled again, you write it as AX2, A2X2, A2M2X2 like that. So there is no prime notation here. Okay. This is equivalent spins in a group here. Here also, of course, there is an equivalent case can come. CH2 here and CH2 here may be equivalent. Then you have to call it as A2 prime, A2X2 prime. That's also possible. You can use prime notation even in weakly coupled case here also. Are you all with me? I hope I'm carrying all of you with me. Now let us analyze this molecule. I want you to tell me what is the Pople nomenclature for this molecule. Remember, there are 2 protons for this CH2. There are 3 protons for the CH3. I'm not worried about carbon. I'm worried about only protons. And these two are well separated. Carbon CH2 comes here, CH3 comes here, let us say. Separated by some 3 or 4 ppm or 2 or 3 ppm. And coupling between these two is very small. I would say it is a weakly coupled spin system. Okay. In which case, what is the notation we have to use? Think carefully. Now what is the notation we have to use? It is A2 or A3X2 or A2X3, whatever it is. This is, I call it A3 because there are 3 protons. I call it X2 here because there are 2 protons here. It is called A3X2 spin system. The notation subscript correspond to subscript refers to number of equivalent protons present in that group. Understand? This is A3X2 spin system. What about this one? Very interesting thing. There are 3 protons here. All are equivalent. I call it A3. No problem. There are 2 protons here. Both are equivalent. I call it, let us say, X2. This only one is left. So equivalent, I wrote the subscript by number. Now, what is the type of spin system it is? Simple logic, it must be A3MX2 and they are very well separated. Chemical shift of this is far away. Here is CH3, then CH2 and CH. Very far away separated. As a consequence, it is A3MX2 spin system. Let us ask you a question. What happens if they were not chemical shifts were not large, they were not well separated? Then what you would have called this spin system? You would have called it as A3BC2 or A3BD2 like that. Because we are writing A3MX2, they are weakly coupled because we know chemical shift is far away separated. If they are not separated, you have to bring the alphabet next to each other. Okay. This is A3MX2. What about this one? Very easy to analyze. We have a CH3 protons. It is A3. This is CH2 and CH2. What do you call this spin system? Very simple. A3M2X2. The reason is nitrogen pulls this one far away. This is X2 and this CH3 is high field, CH2 comes somewhere in between. So I call this as A3 M2 X2 spin system. Okay, very interesting. So far I was telling you about the Pople notation. Now we analyze the spectrum of different spin systems. All A3, A2, AX, AMX we analyze now. That gives you an idea about more about NMR spectrum. Okay. We'll consider number of spins and possible spin systems in the nomenclature. Array, what is possible spin system? I'll come to that. Don't worry, we will go ahead. Let us say I have only one proton in the molecule. Then what is a possible spin system? Only one. Because it can be CHCl3, only one proton. This is either A, X, whatever it is, only one spin. Let us say I have two coupled spin system. Two protons are coupled. What is the possible nomenclature you can think of? Both can be very well separated away. Then they're weakly coupled. They come close by, strongly coupled. Chemical shade separation is much smaller. It becomes AB. It can so happen the chemical shifts will be same, overlap. Then if there is a J coupling, it is AA prime. If there is no J coupling, it is called A2. Understand? AX can become AB, and if there is no J coupling, it will become A2. A2 means it is equivalent. There is no coupling between them. You are not seeing the coupling in the spectrum. There is coupling, but you don't see it in the spectrum. Then it becomes A2. So there are three possible, when there are two spins are coupled, there are three possible spin system, AX, AB and A2. Okay. Now what happens if I take three spin system here? Believe me, there are 10 such possibilities you can think of. It can be start with all the three are equivalent. Chemical shift is same. You will not see the coupling in the spectrum. What is the possible nomenclature for it? A3. If there is a coupling between them which is seen in the spectrum, but chemical shift is same, then what do you call it? A prime, A double prime. You have to use prime notation for equivalence. Chemical equivalent nuclei. What happens if they are very well separated, far away in the chemical shifts, weakly coupled? AMX. If the two are strongly coupled, one is weakly coupled, it can be ABX. All the three are strongly coupled, it can be ABC. If two are equivalent with the same chemical shift, no coupling is seen in the spectrum, another is weakly coupled, it is A2X. These two are weakly, very strongly coupled, same chemical shift, no coupling is seen in the spectrum, but this is also strongly coupled, another proton, it is A2B. So like that, you can start thinking of all possible spin nomenclature. You don't have to worry about it. I have already done it. There are 10 spin nomenclature. Each of them can be analyzed in a different way. Remember, they are not same. Analysis will be different for each of them. We don't want to do that. If I start doing that, there will be a one semester course itself on the Pople nomenclature. We will not do that. We'll simply give one or two examples and go to other things. So now if I go to the four protons couples, you know, believe me or not, there are 33 possible nomenclatures you can think of. I'll just show you the possible nomenclatures. Just we don't analyze all of them. For the sake of giving you an idea of coupled spin system, how to analyze, we will take only two spins and one or two simple example of three spin and stop it. Otherwise, there is no end for it. This itself we can speak for hours and hours, weeks and weeks. I will not go to do that because you have a lot more things to cover later. We have to analyze heteronuclears with carbon-13 NMR, heteronuclear NMR. I would tell you decoupling, relaxation, depth, inept experiment, polarization transfer, NOESY, 2D, relaxation, lot of things I have to teach in the remaining classes. So we don't go into the details. So we'll just take example of one spin and two spin 3 and one or two simple example of this quickly and finish it. With that, we'll really take the spectrum of the molecule in the spectrometer and start analyzing. The spectrum is recorded and available to us. We'll analyze it. Let us see. Now a single spin system. No other coupled spin, no detectable coupling with any other spin, only one spin. How many peaks you expect? Simple. I told you, you will get only one possible peak. Fine. Now, what are the examples of the nuclei which can give a single peak? Look at it. CHCl3 can give one peak. C2HCl3 can give only one peak. Why? Because carbon 13 I assume to be natural abundant and coupling is very weak. You will see only acetylates. When I go to satellite analysis, I will tell you. Chlorine do not couple, which is quadrupolar spin. It generally do not get coupled to proton. Similarly, CCH5Cl2, CFCl3, fluorine. You must get fluorine NMR. If I do, you get only one peak. C6FCl3, fluorine NMR, one. PCl3, phosphorus NMR, you will get only one peak. Platinum 195 NMR, you will get only one. So these are all single spin system. Okay, example of only one spin system without any coupling to other things. Okay, single spin system can also give multiple peaks. This is a very interesting thing. You understand? It appears single, but sometimes I'll give an interesting example. You will be really flabbergasted to see how NMR is so clever, so beautiful. It appears very simple molecule, but gives a 4 peaks like CFCl3. To me it appears like single peak, but in reality it gives me 4 peaks. Right? Where do I get these 4 peaks? But there are real peaks. We have to analyze. I'll give an example like this. Take the example of CFCl3, 470 megahertz spectrum, 4 peaks. All are real. Intensity, this one is 100, this is 95, this is 30, this is 3 intensity. No doubt at all, it's a real spectrum. How do you analyze? And I can assure you, there is no coupling between carbon and fluorine detectable here. They are all satellites. I'm not worried about it. There can be minute peaks like this called satellites when it is coupled to carbon. I am not saying that. This chlorine is not coupled to fluorine. All this thing I am giving you. But still, how I got 4 peaks? Something strange, right? How can you expect 4 peaks for CFCl3 when this is not coupled to this, or 1% natural carbon 13 coupling we don't see, we are not bothered to see. This chlorine will not couple to this, we have only one fluorine. In reality, I must get only one peak, but literally I got 4 peaks. How do you analyze this? All are realistic peaks. I give you the intensity 100%, 95%, 30%, 3%. Very interesting example. What we will do is, we'll come back in the next class and try to analyze these things. That will give you an idea of how beautiful NMR can be utilized in solving many small chemical problems. It's a simple chemistry problem, but you can solve it easily. Okay, so we'll stop for the day. Today I have already given a lot of information about scalar couplings, coupling strengths, and how it can be used using Karpathy equations. And also I brought in Popen nomenclature. How do you represent Popen nomenclature in weakly coupled or strongly coupled case? What happens when there are chemically equivalent spins present? What happens when there are groups of equivalent spins are there, like CH2 protons, CH3 groups are there? How do you represent all those things? And we took the example of spin systems for which we saw what are weakly coupled, what are strongly coupled conditions, and what happens with their homonuclear weakly coupled. What happens if I take heteronuclear coupling, whether it's strong or weakly coupled? Lot of things we understood today. Okay. Now, using Popen nomenclature also, we wanted to know what are the spin system analysis. It's a very interesting thing. We'll continue in the next.